Welcome. The topic we'll be discussing in this lecture is instructions and instruction sequencing. That is, generally in a typical computer, the instructions will execute in sequence. That is, after first instruction, second will be executed, then third, then fourth. It follows that order until and unless there is some disturbance. Like if there is a branch instruction, then this flow may get diverted, or if there is a loop, then this flow may get diverted. So how instructions are getting will execute in sequence, and and when the branch happens, how it gets diverted. So those things we'll be discussing in this lecture. We'll be also discussing different types of instructions, and how it is really executed by converting into simple steps, right? So a typical computer must should able to perform these four types of uh, should able to handle these four types of instructions. Okay. So what are they? So a typical computer should have instructions for transferring data between memory and processor registers. So in processors we'll have registers, general purpose registers. So there should be some set of instructions which is available to transfer data from memory to registers and also from registers to memory. So a typical computer should support these instructions. Then the second type of instruction that it should support is it should support set of instructions for performing arithmetic and logical operations, which is addition, subtraction, multiplication, division, and or not, etc. And also it should include instructions for program sequencing and control. That is the third type of instructions a computer or a processor should support. Program sequencing control may be like a conditional branch. Under this condition, do go to so and so location. So in high level language, normally we use if. So like that, here also we should have some control mechanism. Here in in assembly level programming, we may not have directly if statements, but there should be some option available to change the flow of control. Okay, it is generally the flow is sequential. So but sometimes if we don't want to follow a sequential pattern, if we want the program to jump to some other location, that option should be available. Okay, so a typical processor should also instruction for programming, program sequencing and control. Sequencing is the order in which the instructions executes, and control is to change that order. And as the fourth and the last one, uh, the processor should also include instructions for performing IO transfer. So this is something like transferring data from memory to IO device or from IO device to memory. So these options should be available. So a computer must have instructions capable of performing these four type of operations: transferring data from memory to processor, from processor to memory, and for performing arithmetic and logical operations, and for program sequencing and control, and the fourth one is for IO transfers. Okay, fine. So so next we'll discuss some set of instructions with some examples. So we'll start with something called as register transfer notation. Okay, register transfer uh, notation. That is, see, in a computer, the memory locations will be identified by using some symbolic names. Any memory locations will be identified by using a symbolic name. Okay, say say for example LOC. There is something called as in an instruction. There is something called as LOC. Then it means that LOC refers to some memory location. Okay, so if LOC contains something, if LOC contains 2000, then it means that actually it is not referring to 2000. Yeah, it is referring to that location 2000. It means that the it is referring to the value at 2000. The value at 2000 may be 20. Then it is talking about that 20. Okay. So so the point is, whenever any symbolic name is used, that symbolic name actually refers to the value in that particular location. It is not representing like what that symbolic location contains. Uh, it's not that, it is the value uh, in that location. Okay. But so typically the general purpose registers will be numbered from R0 to Rn. Okay. So when you are talking about general purpose registers R0 to Rn, okay, general purpose registers will be numbered from R0 to Rn. When we talk about general purpose registers, they don't refer to memory location. They contain direct values. For example, if the register R0 contains 20, then this 20 is not a memory location, it's a value. Okay. For that matter, it can be anything. If R0 contains 4000, then that 4000 is not a memory location, it is a value. Okay. 4000 is not a memory location, it is a value. But LOC is a symbolic name which will refer to some memory location. Okay. So as per our textbook, all registers are numbered or named from R0 to R1 or N. Okay. Anything other than that, we will treat as symbolic name, and that refers to memory location. So whenever you refer R0 to Rn, it refers to the actual value stored in this register. But if you say A, actually when you say A, it means A refers to the memory location. It is not some value. Okay. So if so so if A, if you are storing 100, then it means that it refers to the memory location. It refers to the memory location 100. In 100 location, what value stored, so that it refers. Okay, that it refers. Okay. So the memory location we represent by specifying a square bracket. Okay. So for example, when you say within square bracket A, then it means that the value at this particular location. Okay. But even if you don't give this square bracket is not a part of the syntax. It is for our understanding. Okay. Even if you don't give the square bracket also, it means that it refers to the value at the given location. Okay. I think it's clear. So let us discuss these things with some example. Okay. So mm, so for example, when you say this particular thing, uh, contents of a location are denoted by placing square brackets around the name of the location. Okay. So when you uh, so R1, so this means that the content of the memory location specified by LOC, R1 arrow LOC, it means that the content of the memory locations specified by LOC will be moved into R1. Okay. Whereas what this will do, this will add the contents of R1. Now R1 is not referring to memory location. It will add the content of R1 with R2, and the result will be stored in R3. Okay. The result will be stored in R3. Okay. So this is called as register transfer notation, identifying the location of a symbolic name standing for its hardware binary address. Okay. So 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 the symbolic names R0 to Rn, it refers to the CPU registers, whereas anything else, other than R0 to Rn, those symbolic names actually refers to memory addresses. Okay, fine. So say for example, there is an instruction, something like this: move LOC comma R1. Then what does it mean? It means that move the content of the location of the particular memory location to R1. Okay. If LOC is 5000, then and if this particular memory location 5000, and if this particular memory location 5000 contains 10, it will move 10 to R1. It will move 10 to R1. That's the meaning. Okay. Whereas this particular statement, add R1, R2, R3, it means that add the contents of R1 and R2 and store the result in R3. So it means what R1 and R2 are symbolic name, but these symbolic name refers to the registers. Okay, so if R1 contains 2 and R2 contains 3 then it will add 2 plus 3. The content of R1 and R2 will be added and that result will be stored in R3. Okay. Okay. The point is whenever you use registers, they does not refer to the memory location. Okay. That is R1 to R0 to Rn. But whenever you use any other symbolic name other than registers, they actually refer to the value at that particular memory location. Fine. Right. Okay. So there are different types of instructions which we will discuss. In some of the instructions, we'll be discussing some few types of instructions. We are trying to categorize into 3 categories. Okay. In certain type of instructions, what will happen in the sense, the result will go into accumulator. So whenever you use such instructions, generally uh, these are called as single these are called as single address instructions. So in a typical single address instructions, normally the result will go into the accumulator. Okay, and then what you have to do, you have to move the content, move the result from accumulator to memory quite often. Okay, so this is one type of instructions where the result will always stored in the accumulator. And in the second type of instructions, the result will be normally stored in the any of the general purpose registers. So these general purpose registers will be used to hold the operand and also it will be used to hold the register. So by keeping the operands in the general purpose registers, what will happen? The memory traffic will be reduced. If you are not keeping in the general purpose registers, then it means that you are referring to some symbolic name which refers to some memory location. Then accessing data from that memory location will take time. Okay. Okay. So but register bookkeeping should be maintained, like which register contains which value, all these things should be known, right? Okay, so in the first case the result can be stored in the accumulator, the first type of instructions. There is another category of instructions where the result can be stored in general purpose registers, and there is third type of instructions where the operands and the results can be stored in the stack. So this is quite unusual, but we will discuss this. Okay. In the third type of instructions, the operands and the results can be stored in the stack itself. So how all these things works, we'll discuss. So basically there are different types of instructions, instruction formats. So we'll discuss all these instruction formats. Okay. So a typical instruction, what it will have a opcode and it will have some operands or addresses. Okay. Say for example, what is opcode? If there is an instruction add a comma b, okay, then it means add is the opcode. Here add is the opcode. Add a comma b. Okay, it may add a and b and store the result either in a or b depending on the processor type. Okay, here add is the opcode. A and b are operands. Okay, but here I'm using a. So a and b are also addresses, memory address. Okay, if I use add r0 comma r1, then R0 and R1 are direct operands because they are registers. Okay, they are registers. Anything other than R0 to R1, Rn we will treat as memory locations. So here what does it mean? It means that add the content in the location, memory location specified by B with the content in the location A and store the result in the A's content, the A's memory location, in the location specified by A. Okay. But this means that just add the content of R0 with R1 and store the result in R0. Right? Fine. So the 3 address instructions are something like this: add R1, R2, R3. which means that add the contents of R2 and R3 and store the result in R1. That's it. It just add whatever the value in R3 with R2 and the result goes to R1. Okay. And there is two address instructions which are something like this. These are uh, different types of instructions we are discussing. Add R1 comma R2. This will add R1 with R2 and it will store the result in R1. And there is one address instructions add yum. So all these are refers to registers. The moment you say yum, the moment you say yum, it refers to memory. Okay. So the value at the specified memory location. Okay. The value specified by this memory address. Okay. This memory yum will have some number, right? Okay. So if yum contains 2000, it means that the value at 2000. Okay. So the memory specified at that particular address, okay, that will be added with accumulator. Now you are giving only one, so it should be added with what? When you are not giving any other operand, then it means that that will be automatically added with accumulator. Okay, so that's what here in the previous slide we have discussed. The result will go into accumulator. So this is an example of that case. Here you are giving only one operand and that is a memory location. So the content of that memory location will be added with the accumulator and the result also will go into the accumulator. Okay. So such instructions are called as one address instructions. Here we are giving only one address of a memory location. Then there is also zero address instruction. See, this is very interesting. Just if you give add, then what will happen? Just if you give add, then what will happen? Then TOS stands for top of stack. TOS stands for top of stack. Whatever the content in the top of stack, that will be added with the content of top of stack minus 1 and the result will go into top of stack. Okay.